small lecture on the phase diagrams, how to construct the phase diagrams. So we'll end up on the iron and iron carbide phase diagram. So as we have seen this iron carbide phase diagram many times. So what is the how will you define the phase diagram? So phase diagram is like a equilibrium phase diagram, a constitutional map. It's like a world map. Like in a world map, you see different countries have the different borders. So similarly here, different phases have the different borders. They are in equilibrium. So what will gain out of it? Like once you understand the phase diagram, so like where we use this in a real time application. So like whatever we use some materials, steel, in the entire world, more than 80% of material is steel what we are using. So that steel properties, microstructure, mechanical properties, everything will be can be understood from the phase diagram. So now, as a mechanical engineers, we are very attracted towards the mechanical properties of the steel. So how we improve the mechanical properties? So that all dictates by the phase diagram. So that one can tailor the mechanical properties by with the guidance of phase diagram. So similarly, like different steels we have. So if you see the phase diagram, it's a temperature versus composition. So composition, if you see, so there's a different grades of material. Almost now I think 3,600 grades are there in steel grade. So like plain carbon steel, mild steel, austenitic stainless steel, cast iron. So all these different kind of grades are there. So all these for different grades we use different heat treatment. So all that heat treatment how we will do based on the phase diagram. So if you know where is the critical temperature of transformation, so based on that we have to design the heat treatment cycles. So similarly, like for suppose I want to improve the mechanical properties of some material. So I can use some microstructural engineering. So whatever we see physical properties, like using macroscopic mechanical properties, all that is depending on the microstructure, how it is microstructural constituents are there. So when you change the microstructure, mechanical properties will change. So how that microstructure we can change also it will be guided by the phase diagram. So in a welding metallurgy, you know it's a welding, it's like a melting of the metal for joining. So where it will go to the liquid state and solidify to the room temperature. So when you take from solid to liquid to solid, how it will solidify, what kind of phases are there, that also will be known from the phase diagram. So similarly, like material selection, I want to select some material for cryogenic applications. It can sustain such low temperature minus 52 degrees centigrade. So I cannot use mild steel or regular steels perfectly. So for that we have to use austenitic stainless steel. So all this material selection, cast iron, there is a different purpose for the selection of material. So all that will be guided by the phase diagrams. So similarly, failure analysis, any root cause analysis we are doing. So how the crack nucleated, what kind of phases at phase boundaries it is nucleated. All that can be will be guided by the phase diagram. So similarly, casting, if you take very big castings, so how the cast microstructure will be there, what kind of microstructure, how mechanical properties can be made, that can be correlated from the phase diagram. So these are the advantages or application of the phase diagram. So this is the reason we are interested in understanding the phase diagram. So before going to phase diagram, I just want you to emphasize what is the phase, like what we have understanding of a phase. If anyone can tell me.
The composition, this is homogeneous throughout whatever the composition should be, and also the composition should be same.
So other than that,
Atomic
so that is one of the that is part of the definition.
atomic
So vacuum factor is different. So that does not define the phase. Like as we know the state of matter we have, like for just to, if we ignore the Higgs boson and plasma, we can see that just the solid liquid gas classic example. So like we know that these are the different phases, solid phase, liquid phase and gaseous phase. So, so you mean to say this is a phase? Like, can I define this way?
Yeah, solid, separately we can say this area. Solid is,
Correct, but within solid I can get unknown number of phases. Within the liquid also. So like the example is like water it to the kerosene. So they separate together. They two phases separate. So there is a classic definition, textbook definition, the definition too. So it's a chemically homogeneous. So just to, so what is the meaning of chemically homogeneous means the chemical composition of the matter element has to be same throughout the material. So physical properties can be distinguished. For suppose I take two phases, I can distinguish by looking at opaque color, magnetic properties, electrical properties, mechanical properties, whatever the physical properties that can be different for the two phases. So similarly, mechanical properties, two phases will be having different mechanical properties. So the possessing uniform structure and properties. So it is a vague definition, but until unless we go into details, we will not be able to appreciate what is the phase. So in my opinion, what I will say is a crystal structure is the one it can define the phase. So you have a BCC, FCC, simple cubic, and HCP, hexagonal closed packed structure, and DCP. So these are the crystal structures. So in a solid, these are all exist in the solid state. So liquid state, we don't know what is the atomic arrangements. Atoms are mostly brown in motion is there. So we don't know, till now we don't know what is the structure of a liquid. But what we know is the solid, how the crystalline can form by atomic packing in a different fashion. So people define a different crystal structure based on the atomic packing fashion. So those are the one which I will declare. So we know this the classically from the ideal law of gas. We know that as we increase the temperature, solid can transform to liquid. That is so melting can, like after that it can go transform to gaseous. So and even opposite works for the pressure. So what does it say that? Like, do you have any insight for this now? So when you increase the temperature, so solid is becoming liquid, liquid is becoming gas as you increase it. So what is happening is that is phase transformation is doing that. So what is happening is like atoms like you
change in internal energy.
volume is increasing phase. So at low temperature, what is more stable phase?
Solid.
Solid is stable. So in other way, so even like in the solid itself, we know that lot of crystal structures are there. So only 5 have depicted here, but there are many crystal structures are there. So within that, so if you see this thing, packing efficiency, that means how much densely we can pack the atoms within a crystal structure. So if you see that single cubic 52 and followed by FCC 74 and HCP also 72, BCC 16. So just ignore about BCT because it is a variable depending on the carbon concentration. So now out of these is single cubic FCC and BCC HCP. So which one will you assume that at low temperature what is more stable? With increasing temperature, what phases are like in a sequential wise, what transformation can happen? So in a hypothetical situation, we assume that in either, so I have all these, so except simple cubic, I have BCC, FCC, HCP. So out of that, which one? Which one will be at the stable at room temperature? So as you increase temperature, what will be transformed? Can you guess?
Simple cubic will be stable at the room temperature. In case of because of the voids and even of the expansion of the volume also.
So that volume, so density is very less. So packing efficiency is 52. So as a basic law, like law of this thing, at low temperature we have the high packing density should be there. So atoms should be very closer. So as we increase temperature, atoms will become more one. The space will be increased as they vibrate.
FCC, in case of tunnel, it should be FCC. In general, also will be FCC only. As
Yes, that is true, right. So basically at room temperature, more dense packed crystal structures are more stable. That means FCC or HCB can be stable. So as you increase temperature, it can go to DCC and then further any phase, whatever it is. So depending on the phase,
If you increase the temperature, the FCC will transform into some other.
BCC, like whatever
Like it
stable
can transform to
phase.
any. Yes.
So generally what I'm conveying here is at room temperature or low temperature, those packed structures are more stable. So when you increase and the packing efficiency, like low packing efficiency structures will transform to low packing.
If you reduce the temperature, for example, we are considering FCC and reducing the temperature.
Yeah.
So that is also more stable.
No, like further reduce, like that is the maximum packing efficiency. So that is the theoretical 74 is maximum efficiency. Even if you apply heavy pressure and temperature also, it can reduce more than that.
But will it create any problem?
Yes, it will deform.
So that means if we are considering some material for low temperature application, we should go for SC or
So that is so that we confuse actually. So actually, basically, FCC materials people use at low temperature. Even the rocketry, like where people use storage of liquid nitrogen, they use the austenitic stainless steel. Austenitic means FCC. So FCC is very stable at low temperature. Even you can use minus 200 degrees centigrade also. So that is depending on the crystallography. So that will explain it. So this is the so like as of now we are clear that as we increase the temperature, the volume of the system will increase. So as it classically. So the same thing happen in the crystal structure. So that's a general case. But there is a lot going on to construct the phase diagram based on the thermodynamics. We'll see what is the governing equation for this. So, as we know from the first law, second law of thermodynamics, so we can derive these Maxwell relations. So we call it auxiliary equations. So these are basically we have four different types of energies: the internal energy, thermal free energy, enthalpy, and the Gibbs free energy. So out of all these things, so Gibbs free energy is a very profound equation that will give the what is the phase stability. So like we have it so many like as I shown there are many different kind of phases exist in a solid state. So out of all these phases, which one will be the most stable at given condition? So that will be dictated by the Gibbs free energy. So whatever the phase which is having the lowest energy, that will be stable at those conditions. So here basically we change three conditions. So here temperature, and pressure, and composition. So by changing these, so composition I am not writing here, since we are dealing with the only single component system. So for Gibbs free energy will be dictated like if you vary the temperature and pressure and composition. So how the free energy will change, that will be given by this equation. So that is function of entropy and volume. So just before going to this classical Clapeyron equation, I just will show you here. So this is a phase diagram of the single component system. So any material you take, any solid, so it will be look like in a axis of pressure versus temperature. We will have this kind of phase diagram. So where gas is stable and at a low temperature and higher pressure, solid is stable. So similarly, liquid and gas. So but if you compare with the water, we have a water phase diagram for H2O. So we have a similar kind of thing. So what is the difference between these two diagrams? Anybody?
One increasing the temperature in water, the volume will increase.
So increasing temperature because it. No, here only pressure.
Water.
Larger solid zone in simple materials compared to water.
Eight matters solid here in this case, and here it is so
Yeah.
space boundaries less. Other than
So one then up to 4 degrees Celsius. Means, that one,
can you be specific in this diagram? So you mean to say the solid and liquid transformation phase boundary. So this is the pressure and temperature. So I'm increasing. Just assume this is the temperature constant here. So I'm increasing the pressure. So now we have anything to correlate with this.
temperature is constant.
We are increasing the pressure. What is happening?
For solids, when we are increasing the pressure, the curve is shifting towards the temperature. That's right.
Correct.
In case of water, the curve is shifting but it means it is more tends to be solid in case of water.
Exactly. That's very nice. So we basically so as we know just now we spoke that as we upload, as you increase the pressure or decrease the temperature, so the closed packed structures will be more stable, solids will be stable. So as I increase the pressure, this more solid is more stable. That's why it is moving towards the right. So it is stabilizing more solid in this case. But here in the water, what is happening when you apply pressure, it is shifting to left side. That means it is destabilizing the solid. That means it is melting. So when you apply pressure, the water is melting. So that is because there is a reason. You can guess it. Why hydrogen? Hydrogen bond is an element. What else? No, hydrogen bond, just hydrogen bond is it. Anything? No, hydrogen bond is most of the organic compounds are hydrogen bonds. How does it make difference?
Because hydrogen one means people try to make with single molecules, it will not be very
So that is the nature of the methanol and hydrogen secondary bonds. How does it influence this kind of inversion? The symbol
yeah.
this transformation.
More volumes are needed.
Density.
Only of liquid. Like we have solid and liquid. So you mean to say which volume of solid is more in
Hmm.
Volume liquid is more.
So basically density of liquid is more than the solid. So that is the reason we see the
Ice
ice
floats.
is floating and water. And so that is the reason people do skating. So they put a lot of pressure in the sharp edges.
Mm.
So there will be a layer of liquid will be melted. So when liquid melt at the layer, it will be skating like anything. So this is the main reason. So if this is not the principle in case if it is same like other metal. So I think 70% of our air will be around the ocean. Once this Arctic icebergs will melt, so most of the air will be covered with the water. So that is the reason. But why the density is more? Because the packing efficiency of the liquid is more than the solid. So in the solid, atoms will be having the coordination number. So one atom. So coordination number means one atom surrounded by how many number of atoms. So in that case, the coordination number for the liquid is more than the solid. So that is because of the hexagonal crystal structure of solid when it forms. So it is all dictated by the crystal structures, means atomic arrangements, how they do form, and what kind of fashion they do arrange in atoms in the solid state and liquid state. So that is depending on that one, like how phase transformation can happen. So that can be easily mathematically we can show the Clausius Clapeyron equation. So this is, we know that Gibbs free energy is minus ST plus VDP. So at any phase boundary, these like changing the Gibbs free energy 0. So when you take it 0 and you just rearrange it and we get this expression. So where change in the temperature, how the pressure will change. Or other way around, even when you apply pressure, what is the melting point, how it will change at the phase boundary. So that you can write. Here the volume change is generally is positive here. So that is why slope is positive. But here volume change is negative.
Negative.
So because slope is negative, because volume change is negative. So because of this difference in the density of liquid and gas, solid. So this we can write the Gibbs free energy with the enthalpy minus T delta S. So you might have seen the Gibbs free energy expression by explaining it. You heard about Gibbs free energy.
I can't, but exactly what is the meaning is the whole
I'll just explain. So Gibbs free energy is nothing but available free energy for the system to use it to transform or whatever the kinetic, anything can happen. So this is the total energy, the enthalpy, and the T delta is the entropy term. So it's a kind of a degree of freedom. You know what is a entropy? So that means the system will use this energy just to reshuffle itself into different organization, means atomic arrangements. So that we cannot use this energy, we cannot extract from the system. So what we have, the energy is free energies. When we subtract from this one, whatever the remaining energy is there, that can be used for the transformation. At phase transformation, we need some energy is required. So that energy can is dictated by this, what is the difference in this energy. So this is the Gibbs free energy is the main governing equation to construct the phase diagrams. So similar whatever I have shown here, I plotted here for the iron also. So as you see temperature versus pressure, of course axis is opposite. So as you can see the alpha iron is stable here, and like here gamma iron and the liquid and delta iron and epsilon. So can you just I will pose one question, we can think in this direction. So generally what we spoke till now at low temperature, close packed or dense packed phases are stable. So in that case, gamma iron should be here and this should be here. So why the alpha iron, which is just alpha iron is FBCC, so it is 68%, and FCC gamma iron is 74%. So why it is stable at room temperature? Any guess or anything?
It has start. Carbon has start and
That is not mechanical properties.
because of carbon.
Carbon is more soluble in here or here, in fact, more in FCC than BCC. So maybe you can just think of it. You can like at home this one. This is a bit tricky thing, but if you know the concept, then you will understand it. Then we'll go. But whatever we speak till now is the free energy will dictate the equilibrium. So what is the equilibrium? So for suppose free energy versus a different arrangement, atomic arrangements, I see that. So this higher energy, this one, the position and the B type of configuration having a higher energy than A type. So within these two arrangements, A is the most stable. And you can say it is a equilibrium. So equilibrium means the minimum possible lowest Gibbs free energy whichever is having. That is the that is our equilibrium we say. So if it is higher if it is higher energy, so what will happen? It will try to reduce the difference from this and this is the driving force. So if you provide any kinetic energy or thermal energy, so it will atoms will cross this barrier from this to this. This barrier it will cross and it will come to this position. So always nature will go to the lowest free energy. So that is the natural principle. So even in the phases also, solid, liquid, within the solid there are a number of phases are there. So out of those phases, whichever is having the minimum energy, that is more stable. So that is how thermodynamic predictions will be done. So now as of now, we have seen just a single component. That means I have taken only water, I have taken some metal atoms, I have taken only iron, and I see how the phases will change when you change the temperature and pressure. So now I will go to the binary phase diagram. So where you add a different components. That means when you change the compositions, how the phase diagrams or boundaries will change. So I take XA mode, so one element, another element. I mix it, just mechanical mixing of the atoms. So that is when you do just mechanical mixing, you will have this kind of expression. So this is the expression of phase diagram, basically. So this is the governing equation. So this is the when you just add it to difference in this like it's just addition of the two energies of the standard of free energies, and this is the Gibbs free energy. Enthalpy mixing and this entropy condition. So it is like this. So when you write this one G equal to G naught, this is G naught, and delta H minus T delta S is equal. So this is the expression. So out of this, if you see, the most of them are depending on the compositions only. So when I plot like this, so
What is X?
mole fraction, mole fraction. If I take the one element of 90%, another element will be 10%. If I take 50%, another will be 0.5.
For example, we are taking one molecule, one substance is there. So we are taking A amount of that one. So again, we are
No, not A amount, it's some amount of A.
X amount of
A is the type of element, whatever we are taking. So what will happen when we mix these two elements? So it will form some solution, like it's like take some water and sugar, when you mix it, we get a solution. So similarly, we get a solution. But here, the more complicated thing is this one, the free energy enthalpy of mixing. So when you differently shaped atoms inside, how they mixing. So what is the interaction of atoms from one atom to another atom, different atom. So that all depending on the enthalpy mixing. So that is very complicated expression is it. So and people theoretically who calculate from the phase equilibrium calculations, we call it thermocal. And this is the very simple expression, which is the entropy term. So it's basically configuration entropy. Entropy having the two terms. One is configuration, another is thermal entropy. So this is just a mixing of two atoms. We are not heating it to like high temperature or anything to account for the thermal entropy. So when you see this, most of them are function of mole fractions, the composition. So that is why you see the this parabolic nature of it's not exactly parabolic, but kind of parabolic you will get the function. So when you plot this this function, when you change the composition from 0 to 100, how it will change for the solid, how it will change for the liquid, I am showing here. So this is the isomorphous system. I am showing temperature versus composition. So here isomorphous means so it's a completely miscible. So when I take two elements and mix it together, so then they completely miscible. means they mix together, they don't get separated. So that is why even the solid is there. Here you have, for suppose you take here, I have 50% of A, 50% of B. But still I have a single phase. Phase is not separated. So in a single phase, I am getting the both elements are mixing here. So as we know that phase diagram, this is the isomorphous. So where the complete mixing is there, at high temperature liquid is there. So when you come down, so it will transform to solid. And you come more, means you decrease the temperature more, it will completely transform to solid. So there is a phase transformation can happen here. So now just to see how this is being constructed, we will do reverse engineering. So like T1, T2, T3, three different temperatures I will take. At the first T1, what I have is a fully from this end to this end. That means 0 to 100% of B. What I have is only liquid phase, single phase. So here when I plot this one, when with this function, what will happen? The liquid phase will be having the lowest free energy. So when you change the composition throughout this one, the lowest free energy is the liquid one. That is why liquid is stable here. So solid is higher energy is there. So it is not stable. So when you take to two-phase region where liquid and solid is stable, so I will just show you how it is done. So for the liquid we have plotted here, and solid it is plotted here. So up to here to here, up to X, you see this liquid phase is more stable than the solid phase. So here we have a two phases are stable. So we have a common tangent method. So when you do common tangent, it's like equating the chemical potentials of both phases. So you will get the common tangent like this, and within this X and Y, we get the two phases are equilibrium. So when you go just like for suppose higher side, and the this solid is more stable. So it is just schematically it is very nice to show. Just for understanding, I will explain. For suppose I have a one atom, A atom means one element is there. I am adding slow, keep on adding 1%, 2%, 3%. So up to this C1%, Cl percentage. So I have added. So then I have only liquid at this temperature. So like that, at different temperatures we will do plotting and we construct the phase diagrams. That is how we will do construct the phase diagram. So like here and here one more like this is called isothermal GX plots. So at a constant temperature we are plotting the G versus X composition plots. So whatever the lowest energy, that is more stable. That is the bottom line. So when you come here, the completely solid state, we have only single phase is there, that is solid phase, which is more stable. So, but this is isomorphous. For isomorphous, it's the like ideal mixing. Ideal mixing is that the free energy interaction of atoms will not be there, so that the free energy, the enthalpy mixing is zero. So when you have a zero, this is what will happen. When you have positive, you will have a different phase diagram. When you have a negative, you will have a different phase diagram. So everything will be dictated by the enthalpy mixing. So this you cannot change anything. So basically what you are changing is just a composition. Here also just compositions. But absolute means there the values are there, J values, based on the component. But here what is this omega is there, that is the interaction parameter. So we call it interaction parameter, that is very dictating parameter, which will decide what kind of phase diagram will exist for given components.
Gives energy from the liquid. So one gives energy for solid is lower than liquid. One it is the setting. Yes. Another one is not case. Liquid is more and solid is less.
Yes. So what you infer? Just a very good question. So what you understood now, like as you decrease the temperature, so what is happening to solid free energy and the liquid free energy?
first we plot, second plot, liquid, when we are decreasing the temperature at a certain temperature, it is lowest, and again if we are cooling, then it is increasing.
Yes, yes.
With the same as solid. If in third plot, if we are decreasing, it is decreasing, but at a point it is meeting for solid and liquid both. In third plot, for liquid it is more, and for solid it is less. As
That is happening. That is happening. Question is what?
what is the difference? It is different for the
No,
substance.
no, we are increasing temperature. No, substance is same. If we are decreasing the temperature, so what you rightly pointed from the question. What is there is a G versus XP, right? Like composition. So now if you plot this G versus temperature, so always this function will decrease with the temperature. This is either solid or liquid, anything. As we increase the temperature, the free energy function always decreases with the function of temperature. Okay. And that will decrease. So, but what is stable? See, for example, this is the melting point. This is the melting point. And this is the liquid, and this is the solid. So, at this temperature up to melting point, sorry. So up to here, solid is stable, then after this one. So why this is that we will discuss it. So as of now we have seen the isomorphous system. Now we will go to the eclectic system. So when eclectic can form, so whenever this free energy mixing is positive, so that time eclectic can form. So eclectic means, so this is the typical phase diagram of eclectic system. So just a hypothetical, you see this P and B atoms, sorry, different components. So you see that the liquid is stable at high temperature. So when it is coming here, it is transformed into the solid. And once it will come here, this line from here to here. So entirely it is transformed into alpha plus beta together. So whatever the leftover liquid here, suppose. So as we decrease the temperature, so it is liquid. So once it will reach this point, it will become solid. Some small solids will be formed in the liquid. So that solid fraction will increase as we decrease the temperature. So once it will come here, so it will reach up to certain volume. Then this is our solid, and remaining is liquid. So once it will reach, for suppose I have 60% of liquid at this, once I reach this temperature. So all this 60% of liquid entirely will transform to alpha plus beta. So that is simultaneously two solids will transform. That means liquid giving rise to alpha plus beta. So when one liquid transforms to different two solids, we call it eclectic reaction. So that is what it is shown here. So this is the eclectic point, critical point. That means all of the liquids suddenly will transform to two solids. But this is the pro-eclectic. So when you take from here to left side, this is the pro-eclectic we call it. And this is called, sorry, this is hypoeclectic, this is hypoeclectic. And whatever the transformed solid you have from here to here, that is the pro-eclectic. So this is the eclectic point where the liquid completely directly transforms to the two solids. But when you go this left side, the liquid initially transforms to pro-eclectic alpha, and whatever the leftover liquid that will transform again to same like here, two solids it will transform. So from traveling, means not traveling actually, but reducing temperature from here to here, it will produce some amount of alpha, whatever it is there, depending on the equilibrium. So whatever leftover that will transform to this one. So you can say this this here kind of shape. all this transformation will happen in a pro-eutectic fashion. And this is a eutectic. This line is eutectic. But if I choose a composition here, so once I take the liquid, if I'm just transforming it, completely it will transform to liquids. So what is the typical application of eutectic reactions? If you see. That is eutectic, not eutectic. That is still eutectic. So eutectic is there. So eutectic means basically what is happening. For suppose I have this is a melting point. So I take the element, one component A. That is this is a melting point, and B this is a melting point. So for suppose I take this is 1000 degrees centigrade. This is also 900 degrees centigrade. Just assume that thing. So, but I have given two elements to you, two metals. You don't know what it is. So you have two elements. I am telling that this is the eutectic. There is some eutectic point in these two components. Phase diagram. So I have given you two metals. So I asked you to reduce a melting point. So one melting point is 1000, another melting point is 900 degrees. Now I want to bring it to 600 degrees centigrade. So what will
We want to find lowest temperature, lowest melting point.
Yeah, that is what we said. So, for suppose I just mixing of these two elements, 50%, 50%, I will get the lowest melting point, 600 degrees centigrade. Just assume that much. But that is how. So, you reduce the melting point of the system by the eutectic reactions. So, the typical casting. So, castings, like for suppose I am casting size of this mode. So, what I need, every corner, the liquid has to pass through every gate. So for that, the flowability has to be there. So liquid flowability is dictated by the how much melting difference is there. So when I am pouring and when it is solidifying, what is the difference? So if I take the composition here exactly 50%, it is having the very low melting point, and I take it to high temperature and pour it, and it will just flow to the every complex part. So for casting application, this is very. That is why if you see the phase diagrams on the right side, rightmost side, all the cast irons are on the eutectic side. We just quickly go through the thing. So similar.
Let's say hypo eutectic.
This is hypo. This is hypo. This is pro-eutectic. This is also pro-eutectic. This is also pro-eutectic.
It is consequent of and simultaneous.
We did not come yet iron carbide diagram. This is just a hypothetical. We'll explain that. So in that even if you similarly like before whatever we did, similar exercise if you take at a high temperature only liquid is there. So T1. But here two solids are there. So I have to take a beta and alpha and a liquid phase. So the dictating the phase stability will be determined by the ballistic free energy of the existing phase. So for suppose if I take T2, so you see up to here there is this is called the thermal solid solutions. Alpha and beta, they call it thermal solid solution. That means that you have two terminals and the extreme ends we have this composition. So a phase alpha and beta stage like this. So this is there, this corner. Here it is coming here. This is there. So this is the maximum solubility point for the alpha. And similarly beta also maximum solubility is here. For suppose if I have 10% of A, so in this element the maximum alpha, maximum amount of beta for B element that I can add is only 10% on this. Okay, this is all similar exercise we can just go through.
You said that one melting point that is the next to technique point or co-melting. It's possible to increase those.
Yes.
The point or whatever that is the melting point.
Melting point and
Two material combination.
So I will just rephrase the question, tell you correct answer. So here, by adding two elements, we are reducing the melting point. So now you are asking, can we increase also? Yes, we can do it. So that is all depending on the enthalpy mixing. So there is some congruent melting points. Like if you take 9 compounds, stoichiometric compounds. So Fe₃C is a stoichiometric compound. So it's always Fe₃C means always 3 atoms of iron, 1 atom of carbon inside. So it will fix stoichiometrically constant. It won't change the composition. So those compositions will go to highest temperature. So when you have this kind of they call it intermetallic components. So when you have intermetallic compound, they have a highest melting point. You will go to up to melting point. So this is the iron. You might have seen this very familiarly everywhere, but I don't know how many of you have seen this. So you never wonder like why the composition is only up to 6.7%. Why it is basically iron. So what is the difference between iron and steel? They have 1% of carbon, which is not steel.
I ducted cast iron liquid. So things ducted cast iron liquid.
Mechanical properties can be altered anyhow. And give me one material, I will show you the widespread range of mechanical properties. For the same grade, taking one composition here, I can give you 1 GPa yield strength and even 200 GPa. We can alter the mechanical properties.
Basically by percentage of carbon.
Yes.
Difference between iron and
Correct.
steel.
Yes.
So but in 2.5%. About 2.5% is
All these are the steel only. So iron is just pure iron. So
0%.
nobody use a pure iron. So always we use the steel only. So when you add carbon atoms, the iron becomes steel. So, but what is the major difference in terms of mechanical properties of iron and steel? Iron is a little soft, means can say it's a very low mechanical property. But if you add even 0.2% of carbon, it will drastically increase the mechanical properties. Very interesting. You can think of it. So, but we have seen only up to 6.7% of this thing. And also we don't write it. See here composition we are changing carbon. So, but we are cheating that Fe₃C is here. We should have kept carbon percentage. So, you know why that is? I will just show you here. This is the equilibrium phase diagram. So as we know, equilibrium means this is a state where you keep it for infinite time. So even 1000 hours also, it will, 1000 years also, it will be dictate the same phases. So that is equilibrium phase diagram. But whatever we are seeing is a non-equilibrium. Which is, we can say it's a metastable equilibrium phase diagram. So in equilibrium diagram, iron and like you added carbon from 0 to 100%. So this is how the different complex phases can form. So I think iron carbide phase diagram is a very complex phase diagram that exists for any system. So, but as engineers, what we say is that what is the application of, so what we use for the human race. So that only we care about it. So we limited our focus is only from 0 to 6 to 6.65. So only this portion we are interested in. So that is what we see issue. But all this is practically it is not important. So as we increase the higher carbon percentages, so for suppose I go here, so I get it that Fe₃ and C3. It's a very complex crystal structure. What you will get is basically your fracture toughness will go very badly. So it will become brittle. When you just throw the steel very hardly to the wall, also it will break it. So there is no use for the engineering applications. So that is why we limit our focus is only in this range. So this what Chandrasekhar sir was asking. So here sir this 6.67 this is a stoichiometric component Fe₃C. So this melting point will be there up to here. So even it is increased. So here up to here only that melting of heat active. So 1147. But if you see this line, it is extended to almost 1700 degrees centigrade. So you can increase the temperature. So depending on the components what we are adding. So this is a very complex interaction of atoms. How atom is interacting with other atom. So that will dictate entirely what is the stable phase. So coming to this our metastable equilibrium phase diagram. So we have three different reactions here. So as we said, this is the eutectile reaction, this is the eutectic, and this is peritectic. So this eutectic, if you see what we have seen now, 2.14. That means, so this is the maximum solubility of carbon in the austenite. So that is the maximum solubility. So from here to here, this left side, all this is all the family of steels. So we have a so low carbon steel, mild steel, plain carbon steel. So even the austenitic stainless steel. When the austenitic stainless is a multi-component, but the carbon percentage fall within this range. But if you go to the eutectic side, it is the cast irons. So if you see grey cast iron or white cast iron, deliberate. So all those cast irons will come from here to here. So where that flowability is very high, so that we'll get a different complex shapes you can make it. So here, same like the just here it is eutectic is there. That means liquid giving two solids. Similarly, eutectile means nothing but just a solid state transformation. So here one austenite means one solid giving two solids here. Gamma is giving alpha plus Fe₃C, cementite. So two solids it is giving. So this and this have a very similar nature. So but here this happens in the solid state. Here it is liquids to solid state. So this is a peritectic reaction. It happens at 1493 degrees centigrade. And peritectic is nothing but one solid and one liquid, both. Like I have one solid. And this is the system, one solid is formed and surrounding liquid is there. So another solid will form as it will solidify. So this is solid 1, this is solid 2. So solid plus liquid gives to one solid. So there is a peritectic reaction that happens at high temperature. This is also not very important for the engineering applications. Yes, that have some negative impact on the cooling and all, but we don't much deal with this. So our main focus for cast irons, we deal with this eutectic, and first the general steels, whatever steels what we use regularly, this is the reaction what we go through. This is the eutectic. So now we'll just make the same thing whatever I explained, eutectic, and peritectic. So there are different invariant reactions are there, like monotectic is there, peritectile, syntectic, all these in different system, allied system, different reactions are there. But for our restrictions to only phase diagram of iron carbide, only three reactions are there, which I shown here. So we know that iron like alpha iron is having basically BCC, gamma is the FCG, and delta iron is BCC. So maybe somebody can explain why low temperature we have alpha iron, high temperature again delta iron is there. The same crystal structure, but why we are differentiating alpha and delta?
Magnetic property.
Magnetic property, this QV temperature is 736 or something. So if you go above that, it will get paramagnetic. So, magnetic.
In arsenic, it has 8 soluble carbon.
Arsenic.
Arsenic, it has 8 soluble carbon.
You mean to say arsenic having more soluble of carbon? That is true, correct. So that's why you have all these expanded region up to 2.4. How does it explain delta and differentiating alpha and delta? if I have same BCC and both here also BCC, I can name it both alpha and alpha. Like why I'm keeping this delta. So that is where our initial definition of phase. So crystal structure has to be same, composition should be same, physical properties can be different. So the definition we can record it. So here, see BCC like alpha iron having some unit cell of certain unit cell.
It has only one body. It has one. FCC is it has 6 bodies in there.
No, FCC we are not talking about. Only this solid solution alpha iron and this delta iron. So alpha iron BCC, delta iron also BCC. Why we are naming it differently and what is the difference? So if you see the unit cell of BCC. So an atom means all 8 carbons will be having 8 atoms and the middle there will be one atom. So here we have a fixed, this is called lattice parameter A. Might be around 3 angstrom or something, might be this atomic distance. This is typically. So but when you have this high temperature, so this is the high temperature, basic difference is the temperature difference. Here is a low temperature phase and it's high temperature phase. So I have same crystal structure but a different lattice parameter. That means for suppose I'm just giving you a ballpark unit. So this is alpha iron. For alpha iron I have this 3 angstrom. Maybe delta iron will be having 4.1 angstrom. So lattice parameter is different.
Only one phase means one dimension.
No, it is all equal. All dimensions are equal. So that is cubic.
Means 4 will be dimension.
Only lattice parameter will be different. So any guess why the lattice parameter will be different? I told already answer. Here the lattice parameter is small. Here it is higher. So now any guess why that high and low? So why lattice parameter is low for this one? Alpha and high for delta. But space, how you are really? The general cell different. Yes. Yes, that is correct. So basically what you said is correct. I will just explain elaborately. So atoms, like we have two atoms and they suppose I have a set of atoms. So I have a equivalent distance of A for suppose. What does it mean? So every atom has a vibration frequencies around that mean position. So every atom will be, but what we take is the mean position. So as we increase the temperature, that mean will change. The amplitude of vibration will change. So that is how the lattice parameter will increase as we increase the temperature. So similarly, what you said, even internal energy. So internal energy is nothing but potential and kinetic energy of atom. Potential energy, how far they are together, and how much vibration, what vibration they are vibrating. So that also we can answer.
So what are the differences like being state 1 or
So it is not a ductile, rather it will become more brittle. So that is why we try to avoid this kind of delta formation in our analysis systems. So this is a detrimental effect. So what is more advantage you get in terms of strength is from alpha, not to diamond.
High temperature working material will be formed there.
You cannot use material this steel more than, I don't think so we can use more than 800 per unit.
Which one? That delta?
No, iron steel, iron. So there is different class of temperatures, materials based on the temperature. So low temperature, high temperature. So high temperature, what you choose is the nickel based products which used in the gas turbine, where it will go to 1200 degrees centigrade. But in the steels, no application is there above 1000 degrees centigrade. So once it will go 1000, it will become very soft. So there is no structural stability.
Alpha. Alpha will become soft at that temperature.
Alpha will transform entirely to stable, single phase will be. But anyway, once you bench it, you get two phases again. But if you are working only at high temperature, this is a questionable, like we cannot work. It is like a softening of the material. So structural stability will lose. Similarly, cementite is having orthogonal crystal structure, which is a complex crystal structure. So now we'll see, as I explained here, so this electride will focus on the electride. So hypoelectride, hyperelectride. So when you take from here to here left, that is hypo. Here to here right, that is hyperelectride. So we consider these two cases also electride and unwilling. So now we take exactly the eutectide. So similarly, like very low melting point of two solids that are eutectic. Similarly, peptide also. In this phase is more stable up to lower temperature, 720. So if I take this side, what will happen if I arrive at 800 degrees centigrade, start transforming to solid. Similarly here also. But when I take exactly this composition of the steel, for suppose I choose this steel of X percentage, it's exactly the electride point. So I will get the existence of single phase of gamma up to 727 degrees centigrade. So once it will cross this temperature, when you cool down, what will happen? This eutectide transformation will happen. So that means it's like a combined growth of two phases, alpha and Fe₃C. So they do combine and grow. So it's not like one phase will grow, another will be consumed. So both phases will grow and it will consume the liquid. So that is how this is the real optical micrograph of eutectide transformation. Where you see lamellar, we call it lamellar structure. It is having alternating of alpha and Fe₃C layers. So this is the eutectide microstructure, which is used in many applications. Even if you see this ropeways, the cable cars, so which is having a very high strength is required. So it's like a one directional strength is required, not the other direction. It will bear such a heavy loads also because that is because of the structure, this eutectide structure. Similarly, we go to first hypoelectride, so left side. So initially alpha gamma is a, so when you transfer like decrease the temperature, once you come from C to D, what you will say at the grain boundaries, this alpha will start nucleate, it will start transforming. And then you decrease further, the amount of alpha will become more. That is all called proelectride alpha. So once you cross this temperature, so what we will get 100% of mixture of two phases. So this is all equilibrium cooling. Like when you cool it very slowly. For suppose I take small sample of this composition, I take it to 900 degrees centigrade, like switch on the furnace simply. What will happen? It will very slowly will cool. So that time you will see this kind of phase transformations. So this is all equilibrium phase transformations. But non-equilibrium, when you quench it very rapidly or cool it in air or different cooling mediums we use. So we will get a different microstructure. So this is whatever we are talking today is on equilibrium phase transformations. So what you will get here, two different phases are there. Initial transformed protected alpha and the eutectic layers in that lamellar structure. So these both are same, but the way they form is different. So similarly, you can see here. This is all detected, this is detected. So similarly, hyperdetectile also you can see the similar Fe₃C is formed and the same kind of story. But here hyperdetectile, so this is cemented, it's very hard and brittle phase. When you have the higher percentage, generally its fracture toughness will reduce. And the ductility will reduce, it will become more high strength and high hardness. So now we have transformed this proelectric and proelectric hyperdetectile. But now, how much percentage of phases are there? But suppose I transform from here to here. How much proelectric alpha is there? Proelectric cemented is there? That we can calculate by the lever rule. So this is just a cross section of some hypothetical phase diagram for copper and nickel. So where you can see, so for suppose lever rule is basically it's a mass conservation principle based on. So if I come to this temperature, I have a two phases, solid and liquid. I want to know how much solid is there, how much liquid is there. And this is my composition, Z is my composition. How I will calculate? So how much liquid is there? I have to know this segment, M and Z. This segment by this total segment into 100. That is the percentage of liquid. And similarly, how much solid I need, we have to do opposite side. So this Z and N minus the total. So there is that is how we do calculate how much phase fraction is there. Thank you. Any questions, please?